chapter 16, and it's kind of the second part of thermodynamics. And we talked about some stuff that's like thermodynamically relatable type things. I'm stalling until I remember what we talked about. All right, so I'm thinking it's entropy, which is delta S. And delta S, again, has to do with the amount of disorder there is. So as we talked about with delta S, we could calculate the delta S of the universe, which equals the delta S of the system plus the delta S of the surroundings. And we can kind of use that to help us determine whether or not a reaction is going to be spontaneous or not. Remember, as we talked about a number of times, that if a reaction is spontaneous, again, it really has nothing to do with how fast or slow it's happening. It really just means that under those particular conditions, we would expect a reaction to take place without any sort of outside interference to help it along. And that's what spontaneous means. Again, kinetics deals with how fast or slow a reaction takes place, but this is really just talking about that. If a reaction is favored or spontaneous, typically that means the way it's written, products are going to be favored in that situation. And that happens when a delta S is, of the universe is a positive number. It's going to be a spontaneous one. Obviously, if it's a negative number, it'll be non-spontaneous. We calculate both of these things separately. Delta S of the system is equal to basically all the delta S's of your products minus the delta S's of your reactants. So you go to the table typically and add them all up, just like we do with delta H's. We do take the coefficients into account with the values that we find in the tables. And remember that the delta S of the system itself will not tell you if a reaction is spontaneous or not, but it will tell you sort of what's going on in terms of the reaction. Are you increasing the disorder or decreasing the disorder? Again, one of the ways you could kind of predict the sign of delta S, again, is if you create, for example, more gas molecules than you started with, you have a lot more disorder than you started with, and we would expect the entropy to be increasing. And remember that as the entropy increases, that's a more positive value, and vice versa. If you kind of create less gas molecules, for example, than you started with, you're making a much more ordered situation. And remember that delta S becoming more negative in that sense. To do the surroundings, it is related to the delta H of the reaction, is minus delta H of the reaction over the temperature in Kelvin. And again, it's that opposite relationship we talked about. If you have an exothermic reaction, your delta H is going to be negative. And that negative plus the negative that's in this formula will turn your delta S of the surroundings into a positive number. And under normal temperatures, we would expect the surroundings to gain that energy, kind of go a little bit crazy because they have more energy now and a lot more disorder happening in the surroundings. Vice versa, if there's sort of an endothermic process, which is going to suck the energy out of the surroundings into the system, our delta H would be positive. That positive delta H with the negative that's in that formula, again, will turn our delta S of our surroundings into a negative number, which would imply that we're making more order. And that would also be the case as the surrounding loses the energy. Everybody's going to kind of slow down and become a little bit more organized, not flying around as crazily. They don't have as much energy, so it's going to have much more order in that situation. And we would expect the delta S of our surroundings here to be negative. This negative, again, is used in this formula with the surroundings. And again, we sort of see a rearrangement where we may see that formula without the negative in it that comes from a delta G. We then talked about delta G, which is Gibbs free energy. And Gibbs free energy is, again, much like the name implies, it's the amount of energy that's available to do some type of work. There's actually a few different delta G sort of formulas that we've seen. We can calculate delta G of the reaction just like any of the other ones, delta H, delta S, by taking the delta G, and that's sometimes referred to as delta G of formation of our products minus the delta G of all of our reactants. Delta G, though, you can use directly to figure out spontaneity. So if you end up with a negative number, usually that means the reaction is spontaneous. If you end up with a positive number, usually means it's non-spontaneous. We also saw a delta G equation that ties together H and S in this formula here. Delta G is equal to delta H minus T delta S. And remember that when you are using delta H and delta S together, you do want to be careful of units. Again, typical units for delta H is usually kilojoules, delta S is usually joules, and delta G is usually kilojoules. So you do have some differences in terms of factors of 1,000. And remember, you got to kind of convert one versus the other. This also allows us to understand whether or not, we can predict in certain situations if we will have a sort of spontaneous reaction or not, and what conditions would be necessary. Again, for example, if we had a negative delta S and a positive delta H, regardless of what you do, you're always going to end up with a positive value for delta G, so it will be non-spontaneous in all directions. If you have, or all temperatures, if you had a negative delta H and you also had a positive delta S, for example, that positive delta S will keep this back term negative along with the front term being negative, will hit you basically a spontaneous reaction in any temperature conditions. So that's really favorable. Negative delta H exothermic, and an increase in entropy, increase in disorder is very favorable at any temperature for the reaction to be spontaneous. Obviously, the opposite is true. An endothermic reaction is not so helpful when we have also a decrease in disorder. The kind of flow of energy and the flow of disorder are very favorable sort of conditions for reactions to become spontaneous. And again, that's kind of what we see in this sort of situation here. Any questions on any of that stuff there we talked about? All right, so I think we left off with the magnesium example. So I think we're over here, and we are at Gibbs free energy and phase changes. So we touched upon a little bit of this earlier on, I think, in the chapter. But when we do phase changes and when we change the phase of a substance, remember that the temperature doesn't change. This happens at the normal melting point or freezing point of a substance, or the normal boiling point of a substance. And there is some heats of fusion involved. Delta H of fusion is again involved when we do that transition of solid to liquid, or liquid to solid. And again, that value is the amount of heat that's required simply to do that transition, not changing any temperatures, just simply at, for example, water at 0 degrees, which is where it changes. That is like 6.02 kilojoules per mole is the heat of fusion, which is roughly 335 joules per gram for water. And that's, again, the amount of energy that is required to change basically water in the ice form at 0 degrees to water in the liquid form at 0 degrees. Again, a flat line transition in terms of temperature, just changing the phase. We also have a similar one there at the boiling point, which is the delta H of vaporization, or the heat of vaporization is sometimes referred to. That's the transition of liquid to gas, or gas back to liquid. And again, that happens at the normal boiling point. And if you're talking about water, that's 100 degrees Celsius where that occurs. And for something for like water, the delta H of vaporization is roughly 40.7 kilojoules per mole, or around 2260 joules per gram is the amount of energy. You could also see that it takes a lot more energy as you do the transition from liquid to gas than you do the transition from solid to liquid. Again, as you go from solid to liquid, everybody's still relatively close to one another. But as you do that transition from liquid to gas, everybody has to completely break apart from each other and start flying around as gases, or come back to each other if you're going the opposite direction. And that requires a lot more energy sort of input or release to do so. So we can also calculate the entropy of vaporization, or the entropy of fusion, which is the delta S. And we could use our sort of formula there. Our delta G is equal to delta H minus T delta S. Now, when we're at a process of a phase change, that is an equilibrium condition that's happening. basically both phases are in equilibrium with each other. So at 0 degrees Celsius, for example, with water, you have ice and water crystals, sort of liquid water and ice crystals happening. And because of that, remember at equilibrium, our delta G will equal 0. So if we rearrange this equation and solve for the delta S, it will equal our delta H divided by T. And this would be known, for example, if we're doing this transition that's written there, the delta S of vaporization, or the entropy of vaporization. Now, this formula is exactly the same formula when you do this rearrangement as the delta S of the surroundings, except the major difference is this one does not have the negative. Yeah. So very commonly confused both of those calculations. People want to insert the negative in the wrong location. So here you will not have the negative. Obviously, on the one for surroundings, there will be the negative that is there with the delta H. Now, what is this delta H? Well, if we're doing this transition going from liquid to gas, that happens at the normal boiling point, which the temperature for water would be 100 degrees, which if you convert it to Kelvin is where the 373 comes from down there. And this is the heat of vaporization, which is the energy for liquid water to do so. By the way, if you are not dealing with water, you will have different heats of vaporization, different values for the heat of fusion, and you will have different melting points and boiling points for different substances. So if you come across a problem that's not water, you don't want to use these numbers here for water because they're specific for water. You would want to find the appropriate numbers for whatever substances you may be looking for. So as we go from liquid to gas in this case, we can put our values in, and we do end up with a entropy of vaporization of 109 joules per Kelvin. That is a positive number, right? And we know for delta S, if it's positive, that means the order is decreasing and the amount of disorder is increasing. And that's what we would expect as we go from liquid to gas. We're definitely increasing the amount of disorder, and that should increase the entropy value, and we do end up with a positive number. Now, let's say we were doing the delta S of condensation, right? Condensation is basically the opposite move, right? Going from gas back to liquid. And really, if we were doing that calculation for condensation, the only difference is when we do condensation, energy is released, which means our delta H value is exothermic, and our delta H value would be negative in that case. So we would get negative 40.79 kilojoules divided by still our 373 Kelvin, and that's going to give us a negative 109 joules. Again, same number in terms of the entropy, but the major difference here is it is negative. And that also makes sense because as we go from gas molecules that are flying around crazily to liquid molecules, we're increasing the amount of order. And that means that our S value here should reflect that as a negative value, that we're decreasing the amount or increasing the amount of order. Any questions on that there? All right, so let's try one here. The enthalpy of vaporization for mercury is 58.5 kilojoules. The normal boiling point is 600. Okay, let's take a look. So in this case, enthalpy of vaporization is going to happen at the transition of liquid to gas or going in the other direction. We'll assume we're going from liquid to gas in this case. And we are given the delta H of vaporization for mercury, which is 58.5. That's what I was just mentioning. You can see it is a different number than what you have for water. Also, the normal boiling point here, which is already converted into Kelvin, also different than 100 degrees Celsius that we have for water. So once again, this is an equilibrium situation that's happening. So we could use our equation here. Once again, because that's equilibrium, we could set this equal to 0 as delta G will be 0 in an equilibrium situation. Rearranging that, going to bring our T delta S to the other side, and that's going to be equal to H, dividing that over. We get our delta S of vaporization, delta H divided by our temperature. So here we'll go with our 58.5. And also times it by 1,000 just to convert it to joules, because delta S is typically given in joules. And I'm going to divide it by our temperature, which is 630. And again, that's already in Kelvin, so we're good on that. We're going to divide that out. It's going to give us a 92 point, we'll call it 9 joules per Kelvin here. Again, here, this is a positive value. Obviously, if you did not convert it, you would get 0.092-ish kilojoules. This is a positive value, which we would expect here. The entropy should be increasing as we go into the gas phase. As we talked about in the previous slide, if we were kind of doing condensation going from gas back to liquid, the only difference here is our delta H would be negative, and that would give us a negative value for our S. Any questions on that there? All right, so I feel like we haven't talked about equilibrium in a while, and we miss it when we don't talk about it. So let's talk a little bit about equilibrium and the relationship between equilibrium and Gibbs free energy. So we can have a situation where we are not under standard conditions. So remember that when you do see kind of these little knots on all these sort of thermodynamic values, H, S, and G, these are under standard conditions. And what standard conditions, again, basically is if you're dealing with any type of gases, they should be at 1 atmosphere in terms of pressure, or 1 bar. And if you're dealing with any type of solutions and their concentration should be 1 molar. So those are typically your kind of standard conditions. 25 degrees is not technically standard conditions, but it's oftentimes associated with those conditions as well. Now, we could have a situation where we're not under standard conditions, and that is where you would want to use this delta G formula here. This, you could kind of think of this first delta G as the Gibbs free energy, or the free energy under non-standard conditions. This would be our standard conditions. So that's basically your delta G of your reaction, delta G of your products, minus the delta G of your reactants. Those values you would look up in a table, basically. R is our gas constant, and you do want to make sure you use the correct gas constant here. And this is the one that has energy in it, 8.314 joules per Kelvin per mole. Temperature is Kelvin, right? In Kelvin. And then our good old friend Q, right? And this Q is no different than all the other times we've seen Q. It is still calculated the same way as we do K. So this is our concentration of our products, right, with our coefficients divided by the concentration of our reactants. So we've seen a few different types of delta G sort of formulas. This is, again, the one that has anything to do with sort of non-standard conditions. This is the delta G sort of formula that you probably want to use. Now, if you reach equilibrium, or if you're at equilibrium, a couple of things happen to that equation. The delta G does equal 0, and Q would actually be the equilibrium constant at that point. And if you substitute that into the top equation, you get, as you see on the bottom there, 0 is equal to delta G plus RT natural log of K. And if you move that RT to the other side, you get the other delta G equation that involves the equilibrium constant. And that is RT natural log of K. K is the equilibrium constant. T is our temperature in Kelvin. And R is the same gas constant that we have above there as well. So in case you're keeping track, we have something like 4 different delta G type of equations, right? As I mentioned last time, probably the best piece of advice is, depending on the problem, which one you should choose. Once again, if you are just given the equation and pretty much nothing else, go to the table and do products minus reactants. If you have the H and S given to you, drop into that one. If you're under non-standard conditions, hit that one. If you have anything to do with the equilibrium constant, go into that one. So really kind of problem dependent is the best way to kind of choose what would be your right delta G sort of formula to use, depending on the information given to you. Again, I wouldn't reinvent the wheel. If some information is given to you like H and S, don't go calculate it some other way, delta G, use those to calculate it. Any questions on that? That's a lot of lines for this late in the afternoon. We'll take a look at this equation here, which is our delta G equals minus RT natural log of K. And again, just looking at this relationship, remember that, everything should agree. So like our normal relationship, we should have a negative delta G, which means the reaction is spontaneous. And if the reaction is spontaneous, we would expect products to be formed, and that should probably get us a large value for K. So if we have a large value of K, that should end up with a negative value for delta G. And vice versa, if we have a small value for K, that would mean we mainly have reactants. And because we mainly have reactants, that means the reaction is probably not heading to the product side, and it probably would be a non-spontaneous process. So again, all those guys should agree with each other. If you have a K value that's equal to 1, our delta G will most likely equal 0 because the natural log of 1 is 0. And you will have both sort of equally favored reactants and products at that time. So your K value you get should agree with the delta G and vice versa when you're doing these type of calculations. And it's sometimes a good idea just to, double check that, you didn't get, for example, a positive delta G and a really large value of K, because again, those things probably shouldn't go together. You want the right sort of combinations that do go together. All right, let's try some here. Calculate the equilibrium constant for the following reaction. 203 goes to 302. Here's some delta G of formation values you can get from a table. For O3, it is 163.4 kilojoules, and O2 is a grand total of 0. Yeah. All right, so see what you come up with on this one. All right, so in this particular case, obviously something to do with the equilibrium constant, which makes me think I should pull out the delta G equation that has the K value in it, and that would be our delta G naught is equal to minus RT natural log K. Obviously, R is a constant, so that is a value we always have, 8.314 joules per Kelvin per mole. Our temperature here, we need to convert to Kelvin, much like always, so we'll do that little move there. And we got that. We're looking for that. So we do need to calculate our delta G. And once again, we would go to the table and find these values to do it. And our delta G of our naught of our reaction is going to be our delta G of our products minus the delta G of our reactants. And in this case, our products is going to be 3 times 0. And we're going to minus that from 2 times our value there from the table, 163.4. And that is going to yield us here a negative 326.8 kilojoules in this case. Now that we have that, we have everything that we need basically to solve for K. So popping in our numbers there, we're going to go minus 326.8. I am going to multiply it by 1,000 to convert it into joules. The reason for that is R is in joules. Yeah. So again, you have the differences in units. You got to be careful of that. And in this case, negative are 8.314 joules per Kelvin per mole. And our temperature 298, and our natural log of K is K-ish. All right, so I'm just going to take all these guys and divide it over, and that's going to give me 326.8 times 1,000. We're going to divide it by 8.314 and also divide it by 298. We have a negative on the left and a negative on the right, which is going to turn everybody into a positive here. I'm going to end up with a positive. Natural log of K is equals 131.9 in this case. At this point, we're going to E both sides, right, to get rid of the natural log. And that will give us a K That is equal to a 1.9 times 10 to the 57 in this case, yeah. Any questions on that? So once again, it's really important to keep track of those negatives, because if you accidentally left a negative in there, you got a much, much different answer, something with a negative exponent, which again is why you should think about your answer to make sure it does make sense. In this case, we have a delta G that is negative, which would imply this reaction is spontaneous and heading to the product side. And that means we should have more products than reactants, and we should end up with a large value of K, which that would definitely qualify as a large value of K in this case. Any questions on that there? Also, depending on rounding, sometimes when you do the kind of the E of stuff, you might get a slightly different front number depending on where you kind of rounded the number and stuff like that. All right, let's take a look at another one here. Calculate the delta G naught for the following. Okay, so looking at this one again, we're giving equilibrium constant. So again, the same sort of formula would be probably our best choice there. And at this point here, we convert that into 298 Kelvin by adding 273. And we basically have now everything on the right-hand side here, minus 8.314, which is our K value, our temperature 298 here, and our natural log of our KSP. Remember, doesn't matter what type of equilibrium constant value it is, they're all the same. They're all K values. So if we do that there, 8.314 times 298 times a natural log of 1.7 to the minus 6, and the negative in front will give us a 32914 joules, or about 32.9 kilojoules in this case. Again, here things hopefully do make sense. I have a small value of K, which means I mainly have reactants, which would probably mean I should end up with a positive value here for delta G, because this reaction is probably non-spontaneous, going to kind of hang out at the reactant side versus the product side in this case. Yeah. Any questions on that there? All right, one last one here for this chapter. Delta G naught for the following reaction is 2.60 kilojoules per mole at 25 degrees Celsius. In one experiment, you had initial pressures for hydrogen, that's 4.26 atmospheres, iodine, that's 0.024 atmospheres, and HI, which is 0.23 atmospheres. What is the delta G for this reaction, and which way will it head? React. All right, let's take a look. So, a couple of things here. Obviously, we have delta G not given to us. Delta G is what we're looking for. This is the key right here. When we look at the pressures, these are not 1 atmosphere, and this is sort of our non-standard conditions is our pressures here. So then that should point us to the direction of the only equation that has kind of 2 delta G's rolling with it, plus an RT natural log of Q. Remember as well that this is a plus, and people always want to subtract that little guy right there. All right, so obviously here the delta G naught was given to us. If it wasn't, by some chance, you would go to the table and do products minus reactants again. That is how you would get to it. So I think we got pretty much everything we need. We got our temperature we need to convert to Kelvin, so that's going to give us a 298. And now we could go, our delta G here is equal to our delta G naught. That's going to be 2.60. I am once again going to multiply it by 1,000 and convert it to joules. Once again, the reasoning behind that is right here. The R value is in joules. So it doesn't really matter how you convert it, but you don't want to leave one in joules and one in kilojoules. Otherwise, you're obviously going to be off by some factor there. Our temperature going to be 298, and we're going to go natural log of Q. So remember that Q is calculated the same way as we do K. So in this case, it would be our pressures actually of HI, and we do need to square it, divided by our pressure of H2 and our pressure of I2, which again, if we put it in here, our HI is 0.23 squared. Our H2 is 4.26 and 0.024 for our last one. That is going to give us a Q, it looks like, of 0.23 squared divided by 4.26 and divided by 0.024. Looks like a 0.51741. So that would go right about there, yeah. All right, so all that's left is to punch all that into the calculator, right? So we're gonna go natural log of our number there at the end, 0.517. We're then gonna times it by 298 and times it by 8.314. That's gonna give us, I think, when we kind of do this side, minus 1632.5 joules to go with this guy. So now we're gonna add them together, 2.6 times 1,000 to put everybody in the same unit, plus what we got there, negative 1632.520879. And that's going to yield us a delta G here of 967 joules. If you went kilojoules, obviously you're at 0.96 in this case, kilojoules. Any questions first off on the calculation here? Now, because our delta G is positive, that would mean that we would expect this reaction to hang out towards the reactant side, right? As it is going to be non-spontaneous and reactants are going to be favored versus products because it's not going to head to the right there. Any questions on delta G here? All right, that wraps up this chapter. Congratulations. That's chapter 7 and 16, also known as the exam a week from Thursday. Yes, that's good stuff. I feel like we just took one. I know it is because you just did take one. All right, we're off to the next. So we are off to chapter 17, which is, I know some might be thinking I'm joking, but I'm really not, just so you know. So chapter 17 is electrochemistry. This starts chapter 3 material here. So we're going to talk about electrochemistry, and we're talking about galvanic cells and a bunch of other stuff. We are going to kind of review, which might be review for some people. Probably if you took me, it's definitely review. But depending on who you had for 200A, maybe it isn't review for you. So just to make sure everybody's going to be on the same page in terms of redox reactions, how to balance redox reactions, how to identify oxidation numbers, all those favorite things you loved from those labs that you did in 200A, those study assignments. You didn't love those study assignments? To really send your complaints to Professor Wada, right? No, I'm just kidding. All right. So electrochemistry here, it's all about redox reactions, and redox reactions basically means oxidation and reduction, and they do occur together. It is basically a transfer of electrons that's going to happen in this situation. And as we will talk about, this transfer of electrons can be used later on when we talk about galvanic cells. And it really, in some sense, batteries as well can be used to power things and power devices. When we talk about something being oxidation, oxidation usually means that it has lost some electrons. And reduction usually means that it has gained some electrons. And some people like to go with Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Nowadays, people are fond of the oil rig. Oxidizing is losing, reducing is gaining. Throw Leo the lion on the oil rig, he goes grr. You don't have to choose. You could just use everything together. And nice little situation in that case. So what happens when these processes occur? The oxidation number or the oxidation state of a element or substance changes, and sometimes people have a hard time figuring out, is this thing being oxidized, is this thing being reduced? And there's really a simple sort of way that you could do it if you could correctly identify sort of the oxidation number of the element on the left hand side of the arrow versus the right hand side of the arrow. And you can just use a basic number line And usually there's positive numbers to the right of 0 and negative numbers to the left of 0. And when somebody loses electrons, they now have more protons than electrons, so they become more positive. So if you look at somebody's oxidation state from reactants to products, and they're moving along the number line towards the positive direction, that thing is going through oxidation. If you gain electrons, you now have more electrons than protons, which means you're becoming more negative in that case. So if you look at the oxidation number and the thing is becoming more negative or moving towards the negative side on the number line, it is going through reduction. So if you had something like an iron 3 on this side and an iron 2 on that side, obviously, the charges here are the oxidation numbers of these ions. We have something that started at +3, ended at +2. If you roll over here to the number line, +3 is over here, ending at +2, which is in this direction. It is moving in the negative direction. This guy is going through reduction in this case as we follow the actual change in oxidation state, right? Just like if you had a sodium on this side metal that went to a sodium with a +1 charge, that is an oxidation state of 0. That is an oxidation state of +1. That would be the sodium starting at 0 and ending at +1, heading towards the positive direction. And this guy would be going through oxidation in this case. So that's a very simple way. If you can correctly identify oxidation numbers, just kind of see which way it's going, and you can very quickly identify what is being oxidized and what is being reduced. Any questions on that there? All right. So as I mentioned before, in electrochemical processes, oxidation reduction always occurs. And one of the nice things also about oxidation reduction is they always occur together, which means if you're able to for sure figure out one thing, like that's being oxidized or that guy's being reduced, then the opposite thing's happening to the other species that is present. Those electrons will go out and do some type of work, like power your device. Like when you look in a battery compartment, there's little wires, and those are electrons moving around those wires to power your device and come back in. Now, if we take a look at this reaction here, a little synthesis reaction, which is a redox reaction. If we look at the oxidation states of everybody here, anybody by themselves, naturally, the way they come, that's uncombined, has no charge or 0 oxidation state. That is also the 0 oxidation state for oxygen. That is naturally how it comes as a diatomic molecule. Things only get charges, as you know, hopefully, when they hook up. Metal and non-metal is basically when they kind of pick up charges, and also when they start sharing electrons with other people. And in this situation, this is an ionic compound where magnesium's group number 2 has a +2 oxidation state and oxygen has a -2 oxidation state. So once again, if we want to kind of figure out what is going on in this situation, we could have referred to our number line here. And if we look at the magnesium on the left is starting at 0, and the magnesium on the right is ending at +2. So the magnesium here is going through oxidation. By the way, by default, that would mean that the oxygen here is going through reduction, but you could also do the same thing for oxygen. Oxygen on the left-hand side is 0, and on the right-hand side is -2, which means it's moving in the negative direction, and it is going through reduction. And we should always know this situation because this is a very important situation. This is a metal and a non-metal coming together, and that is the basis of a ionic bond, right? And always metals lose electrons in that situation, and non-metals pick up the electrons in that situation. So whenever you have anything that's forming an ionic bond, and you have a metal and a non-metal coming together like this reaction here, the metal should always be the one being oxidized. The non-metal should always be the one gaining those electrons. We can write 2 reactions, which are referred to as half reactions, because they frankly are half of the overall reaction that is taking place. One is an oxidation half reaction, and one is a reduction half reaction. Now, the oxidation half reaction is basically the magnesium going to magnesium. So again, it's going from 0 to +2 here. And it's going to give off 4 electrons in this situation. And because the electrons are on the product side, that is typically where we find electrons in a oxidation half reaction like it is being given off. Why is there 4 electrons? Because each magnesium will lose 2 electrons, and there's 2 magnesiums. So that's a grand total of 4 electrons. 2 for each magnesium is going to give it up. On the other side, we have the oxygen gaining those same 4 electrons. So it is the exact same 4 electrons that go to the other side. And that's going to be the reduction half reaction. And on a reduction half reaction, we find electrons on the reactant side. Now, these are, again, half reactions because, like I said before, if you take these 2 half reactions, basically, and you add them together, when you add these half reactions together, the first thing you should always make sure before you add half reactions together is the number of electrons in each half reaction is the exact same number. If they're not the same number, it may sometimes require you to multiply a half reaction by a number, or maybe both half reactions by a number. But you always want to make sure before you go to add these together that you have the same number of electrons. And that is because the electrons should always completely cancel out. So when you add these reactions together, anything that are on opposite sides of the arrow will cancel out or reduce. Here, the electrons completely cancel out, and we are now back to our overall reaction. Everybody on the left stays there, everybody on the right stays there, and this is going to make our ionic compound. And now we have the overall reaction that is taking place here. So when you write half reactions, you want to make sure you display the electrons on the proper side, and again, that tells you whether it's being oxidized or reduced. Any questions there? There's our half reactions added back together. Now, here we could also look at an example of this. And again, if we look, we have calcium, which is naturally how it comes. Oxidation state of 0, oxygen is 0. Once again, when we make this ionic compound, the calcium is going to end up at +2. Oxygen is going to end up at -2. And again, as we would expect in this situation, our calcium here starts at 0, ends at +2, becoming more positive. So it is going through oxidation, are being oxidized. Our oxygen, once again, starting at 0 and ending at -2, becoming more negative. So once again, it is going through reduction in this case. We could write our 2 half reactions. As you can see, again, we got the same number of electrons on each opposite sides. And when we cancel out the electrons, we do get back our overall reaction there of our 2 calciums plus our oxygen, making our 2 calcium oxides. These are synthesis reactions, which are redox reactions. By the way, synthesis reactions, decomposition reactions, single replacement reactions, and combustion reactions are all redox reactions that are happening. They are all basically electrons being transferred. And as you may remember, electrons being transferred is one of the 3 reasons why a reaction takes place. Electrons being transferred. The other 2 reasons is you made a solid or you made water. Those are the 3 main reasons why reactions take place. Now, in addition to what is being oxidized and what is being reduced, there's also things in this that are called oxidizing agents and reducing agents. So the oxidizing agent is actually the substance that gets reduced, while your reducing agent is the substance that gets oxidized. They are sort of opposite of their names. The reason they're opposite of their names is they cause that effect in the other person or the other substance. So if you are getting reduced, that means you need to gain electrons, and the only way you can gain electrons is you got to cause somebody else to get oxidized. So that is why the oxidizing reagent gets reduced, and vice versa. If you are going to get oxidized, that means you're going to lose electrons, which means somebody else has to gain electrons, and that person is going to get reduced in that case. So once again, if you're asked what is the oxidizing agent or the reducing agent, that is a different question than you're asked what is being oxidized and what is being reduced. So again, those are different questions. In our previous examples there, you can see there that the calcium and the magnesium were both being oxidized, and those would be our reducing agents. And in both cases, the oxygen was being reduced, and that would be our oxidizing agent in both of those previous examples. So all four of those things, if you ever asked to identify it, what is being oxidized, what is being reduced, the reducing agent and the oxidizing agent, they are all found on the reactant side of the arrow. The left-hand side is where you find all those guys and identify those guys from. Now, in this particular case, there are a couple of other definitions of oxidation reduction, which we don't necessarily use all that much in this class, but if you're continuing on to organic, you will perhaps use those definitions. So oxidation, typically you look at losing electrons, but it can also mean that you have gained oxygen from reactants to products, or you have lost or lose hydrogen from reactants to products. Reduction has similar sort of definitions. Reduction means that you gain electrons, but it can also mean that you have lost oxygen as you go from reactants to products, and you gained hydrogen as you go from reactants to products. Like I mentioned a second ago, these definitions here of hydrogen and oxygen is typically used a lot in organic chemistry. And that is because in organic chemistry, it's all about nonmetals. So there's not a lot of metals and electrons sort of being transferred in that sense. So a lot of times they look at oxygen and hydrogen rather than electrons being sort of transferred. And those are two definitions that you typically will see in organic chemistry. You could also apply it here. Again, if we look at the carbon on the left-hand side, has no oxygen. On the right-hand side, gains some oxygen. And obviously it gains some oxygen. So this is being oxidized. By default, this guy is being reduced, where you can see he has oxygen and then lost oxygen as he went to the other side. That would mean that the carbon in this case is our reducing agent, and the tin in this case is our oxidizing agent in this particular case. So again, we won't see too much of those definitions in here. We mainly will stick to the electrons gaining and losing. But down the road there, if you go to organic, you will definitely see a lot more of oxidation reduction involving oxygen and hydrogen. By the way, in this particular case, we actually had a metal there, which would help us figure it out if you weren't sure. We could look at the tin here. The tin on this side is a +4 oxidation state. The tin on this side is a 0 oxidation state. So if you roll to your number line here, tin is starting at +4 over here, ending at 0. It is becoming reduced in this case, becoming more negative. And again, you could have figured it out still that way by looking at the tin in this case. And by default, the carbon would have been oxidized because it would be the opposite thing that happens. Any questions on that there? So let's talk officially about how we identify oxidation numbers. Again, they are sometimes referred to as oxidation states as well. And a reminder that the oxidation number or the oxidation state is not always going to be the charge that you associate with certain elements, especially in an ionic compound. So if they are in an ionic compound, things like fluorine, chlorine, bromine, those guys will have their normal sort of oxidation state numbers that you associate, like -1s, obviously in that case. Now, when those type of elements are not in an ionic compound and they're in a covalent compound where they're sharing electrons rather than electrons being transferred, things that we normally associate with a negative charge can have a positive oxidation state. Like, chlorine could have a +5 oxidation state or a +7 oxidation state rather than a -1. So oxidation state is not exactly the same thing as the ionic charges we associate with elements. First rule is any element that's by itself, naturally the way it comes, will have an oxidation state of 0. Any ion that is monoatomic, the oxidation state will equal the charge on it. So earlier we had like a iron 3 and an iron 2. Those would be the oxidation states in those situations. A good place to start is oxygen. Oxygen is usually an oxidation state of -2. The one exception is when it is actually peroxide, it is -1 instead of 2. And that would be like something like H2O2. This guy would actually have a -1 oxidation state because that's actually peroxide rather than oxygen. How do you know it's peroxide versus oxygen? Usually whatever is attached to will have that kind of extra 2 in it. And that's how you can kind of tell sometimes it is. I would say probably 99% of the time it's going to be just regular old oxygen with a -2. But again, if you have something like hydrogen peroxide, sodium peroxide, you can end up with one with a -1 charge. When we look at hydrogen, hydrogen is typically +1, except if it's bonded to a metal, and in that case, it's going to be hydride, which is -1. So again, if you had hydrogen that came after a metal, that's going to be a -1 oxidation state for it, like it is the hydride ion, rather than a +1 that you would have typically. Everybody in group 1 will be +1. Everybody in group 2 will be +2, and fluorine will always be -1. When you add up all the oxidation numbers, they do have to equal the overall charge on the compound or the ion. And if that overall charge is 0, you need to have everybody add up to 0. If the overall charge is like -1, everybody needs to add up to -1. So if we take a look at our bicarbonate here, when you have a 3-pack of elements here in a formula, usually the good idea is to go right, go left, and leave the one in the middle for the end. And if we did that, we would go -2 for our oxygen. -2 and 3 is a grand total of -6 charge. Going to the left-hand side, that is hydrogen, which should be +1. That would be a +1. Remember that this overall thing equals -1. That means in this particular case, our carbon is going to roll with a +4 here, oxidation state. So that will give us an overall -1 charge. And that would mean that the oxidation state of hydrogen would be +1. The oxidation state of carbon would be +4. And the oxidation state here of oxygen would be -2, not the grand total. So when you're given the oxidation states, our numbers is just the individual element by itself, what it is. In addition, you do need to include the charges. That includes plus or minuses. So when you write oxidation states or numbers, they need to have the pluses or the minuses in there as well. Any questions on that there? All right, so let's try these here. Let's do the oxidation state of each of the elements in each of these guys, what they are. So take a few moments there and see what you come up with. Okay, look here and see. So we'll start up here. So starting with oxygen, -2 looks good. And lithium is group 1, so it will be +1. So the oxidation state of lithium +1, oxygen is -2. Taking a look on PF3, fluorine is always going to be -1. There's 3 of them. That gives you a -3. Overall charge here is neutral, which means the phosphorus here is going to roll with a +3 oxidation state. So our phosphorus here would be +3, and our fluorine would be -1 in this case. Again, that equals 0. Now, again, you may think, like, isn't phosphorus -3? And it is in an ionic compound here, but once again, it is not an ionic compound. So our phosphorus is hooked up with 3 fluorines. And as we know, fluorine is the most electronegative atom you could have. So when they're sharing electrons, the electrons are being sucked towards the fluorines, and that's making phosphorus more and more negative as those electrons are going to be closer to the fluorine because it's more electronegative. And that's why in this situation in covalent bonding, our phosphorus takes on a +3 charge rather than a negative charge because those electrons are going to be kind of sucked away a little bit from it. Over here, we have nitric acid, -2 for our oxygen. That gives us a -6 overall. We do need equals 0 when it's all said and done. +1 for our hydrogen. And in this case here, our nitrogen going to take on a +5 oxidation state to get us to 0. So hydrogen being +1, nitrogen here +5, and oxygen here being -2 in this case. Once again, if you just kind of sketch nitric acid, looks something like this. And same idea here. Oxygen is more electronegative than our nitrogen. Going to kind of suck those electrons away from it. Going to take a more positive oxidation state here in this bonding. Over to our dichromate, -2 for our oxygen. That's 7 of them. That's like a -14. It does need equal -2 when it's all said and done. Our Cr2 there, we have 2 of them. That means each is like a +6, which would give us a +12 overall. So here our chromium going to be +6 and our oxygen -2 in terms of its oxidation state and number. Any questions on assigning oxidation states? Really important outside the balancing and the redox, but this is really important, especially when we get into galvanic cells, to understand assign oxidation numbers and understand who's being oxidized, who's being reduced. Really important for that part of it. Any questions? All right, we will lay it up there for today.